thanks to coming to our special EDS Seminar series focused on our first cohort of working groups at ESIIL. Today we're joined by Meyer and Rachel Pilla of the Freshwater Zooplankton Working Group. Michael is a research ecologist at the U.S. Geological Survey based in Portland, Oregon, and Rachel is an aquatic ecologist in the Environmental Sciences Division at Oak Ridge National Laboratory. So welcome, both of you. We're so happy to see you, and I'll let you take it away.
Cool. Thanks so much. And thank you so much, ESIIL, for hosting us twice in person and for hosting this seminar. It's been really fun, and at least on behalf of the working group, Rachel and I are really excited to share some of the greatest hits that we've put on during this working group meeting. So to start things off, we're going to talk an hour about zooplankton. Not sure how many folks. So that's going to be really fun. And largely, I feel like a lot of the working groups say this, and I really just want to emphasize ours especially would not be possible if it wasn't for the contributions of so many folks. So here we have many of the folks that have been involved in our ESIIL working group, but we've also been fortunate enough to be supported by the USGS Polysynthesis Center in Fort Collins, CISAB in Montpellier, France, and also the Global Lake Ecological Observatory Network. And what I mean by that, it's not just the support of who's been helping with each of these working groups, but who has been ultimately contributing part of their data to help make these syntheses work. And so these are a list of all the institutions involved in these larger data efforts. And it just keeps going over 2 slides. And ultimately, you'll be seeing these little infographics or cartoons in some of the slides. There's really 3 main projects, and I'll talk a bit about this more throughout the talk. Zoo Size, which is looking at zooplankton size metrics, so that's their logo. The ZIG, which is the Zooplankton International Geospatial Dataset, has this logo, and then Zeus, which is understanding the space for time substitutions with zooplankton. So we've got those cute little logos up there, and we've started our own little ZIG universe. So be on the lookout for even more zooplankton related images. But getting into what have we been able to do assembling all these data from this larger network of collaborators? I think we've been able to speak to the conversation about freshwater biodiversity, and I think we hear about this a lot, how biodiversity is certainly changing. Many times we hear that it's declining, in decline. And freshwaters especially are kind of like this wild, wild west in the biodiversity space. There's been many Herculean data efforts to assemble and harmonize time series of biodiversity. Here you can see this infographic or this image from Biotime. And one thing that really jumps out is that marine and terrestrial systems tend to be more represented in these global compilations relative to freshwater ecosystems. And this mismatch is potentially really important, as freshwaters account for about 2% of Earth's surface, but also more than 33% of vertebrate, and also more 50% of fish species are occupied in freshwater ecosystems. And there's some evidence that freshwater biodiversity may be outpacing these other 2 ecosystem types, that is the terrestrial and the marine ecosystems. But when we really dig into what global assemblages or extensive assemblages we have for understanding biodiversity change, that sliver of freshwater ecosystems tends to be more heavily biased towards vertebrates, so the fish taxa. And this is important because it's not just vertebrates, it's not just fish that are in these freshwater ecosystems. We also have zooplankton, or more broadly, I would say invertebrate taxa as well. that makes up potentially a lot of that biodiversity change. And these zooplankton are exceptionally diverse. They have a range of body size, feeding strategies, habitats, reproductive capacities. And we largely tend to think of these as being in some of these three groups. The copepods, so they're on the left. We have the cladocerans, so things like Bosmina, Daphnia, Bithotrepes, spiny water flea, and then also the rotifers, so those non-crustacean zooplankton. And I feel like there's always this, I myself have been thinking about this, like what, we've put a lot of time certainly into understanding zooplankton community composition and community change, but especially, how do we think about zooplankton change in respect to the larger ecosystem where we have done a lot of work, and I think that the way that I talk about it, at least, is zooplankton play this really critical ecological function, as they're kind of like in the middle of the food web. They're responding to those higher level pressures as well as lower level pressures. And so they're really integrating those bottom up and top down processes. And it's through understanding zooplankton that we can also get at how all of those processes might be influencing the whole lake ecosystem. They also tend to be pretty sensitive or responsive to water quality conditions. So that makes them, sometimes reliable indicators of things that might be changing within a lake ecosystem. Those changes that maybe we're really interested about from the perspective of a regulatory framework, or those big shifts that we're all really concerned about. Sometimes they might be able to signal those changes before the change actually happens. And while they're usually not included in the regulatory process themselves, they tend to be really important, at least for supporting those types of changes, especially getting at the biological responses. And I think this is sort of like the unspoken or the less talked about thing, is that, a great example of this is their connectivity with fish. They tend to be a main conduit for fish bioproduction. So things like Lake Michigan, the Great Lakes, where there's super large economies and cultures around fish production, and zooplankton can sometimes signal when there's going to be changes in fish bioproduction, even before we see that fish bioproduction or a change. And so, one thing that we tried to emphasize in this talk is, not only talking about what we did, but also the story behind how this working group got started. And, for folks that might be less, so hopefully I've made a case that freshwater biodiversity might be important. We might not know less about it than we think that we do. It might be changing. And also, there's some particularly sensitive or social, cultural, economic hotspots that we might want to know about. And zooplankton might be at the center of it. So, a bunch of us at this GLEON meeting. So GLEON basically works where we have these sort of working groups that meet to talk about what really excites them about big research questions in lake science. And in 2019, at this meeting in Ontario, a bunch of us were sitting around a table just like that. I think this picture was taken at that meeting. And we all realized, we were all interested in synthesizing how zooplankton are indicators of ecological change. And this ultimately led to the formation of about 3 groups where we all kind of recognized that we were, wanting to at least solicit similar types of data from the larger GLEON community. But it might be better to work as a team and synergize rather than going about it independently. And so in 2019, that's where the ZIG dataset or the ZIG zooplankton as indicators at the time was started up by myself, Steph Figueri, Rachel, and Warren Curie. Zoost was started up by Jason Stockwell, and ZooSize was started up by Rosalie Bruel and Zeynep Ersoy. And, and we were all talking about how could we assemble these sort of global zooplankton data sets that would allow us to get at the types of questions that we all and many others were interested. And can we address complementary questions with these types of data sets? And some of those overarching questions, we're looking at global distributions of zooplankton community composition, both through the perspective of biodiversity and biomass, or biodiversity and biomass. That was the main emphasis of the ZIG data set. Zoo size was more interested in understanding sort of the how zooplankton size distributions changed across some of these bottom up, top down pressures. And then space for Zoost, the space for time substitutions, was ultimately saying, we're really interested in long temporal changes, but we tend to make our understanding tends to be based off of these sort of snapshot surveys over large spatial gradients. How valid are those sorts of surveys, and what is the reproducibility of those types of surveys? So that was the main goal of Zoost. And the way that we went about building a lot of these data sets, so at least for Zig and Zoost, and this is pretty typical for many Gleon projects. We started the embryonic stage in like 2019, and then we moved into 2020, started figuring out what were the real goals of this product, what were the questions that we wanted to get at, and then also creating an internal governance or policies of how is co-authorship declared, how is earned, how are data shared, how are data handled once they're shared. And then we put out a massive data call, including a little community news piece in LNO Bulletin, trying to get a really wide call for folks that might have these sort of zooplankton community composition time series. And then that's when the grunt work happened. So I would say this probably started about 2021. A team of about 30 data harmonizers went to put out a data set, or went to work with each of the contributed data sets, shaping them into a consistent format and making sure that all of the data that were reflective within a data set were consistent across all the data sets contributed. And I'm very happy to say that this year, what started in 2019 is finally real. The harmonized data set is finally published on the Environmental Data Initiative, and we can talk about that a bit more. I'm also happy to say, I know it's on another slide, and I think it's on another slide, but our LNO letters data paper for the ZIG data set was accepted last week. And I'm really glad. Yay! So there's about 130 co-authors. It's certainly the largest project that I've been a co-champion of. So that's good things can happen. It takes 7 years. Now, a parallel effort was this zoo size data set that was really getting at individual body size data. So they put out a separate call in 2020. They were receiving data from 2021 to 2023. They conducted or are conducting a similar harmonization process. They've got their own workflows, and they're about 90% complete at this stage. So hopefully at a future ESIIL seminar, they can share their zoo size reports or report back. And just to give you folks a high level understanding of what's included in these data, given that these were complementary calls, we have complementary info for many of the lakes that are included in both. So standard water body information, everything that is in black text was mandatory. Everything that's in red text was optional. So if they had it, they could contribute it. So there's various locational and morphometric information. There's water quality constituents like temperature, nutrients, chlorophyll, sampling methods. Those can vary widely. And zooplankton, they had to contribute at least density data. So at least the count data, biomass was optional. And the ZIG data set is a time series data set, whereas zoo size is more of individual body sizes It had to be once per year with a minimum of 1 year of sampling. And then they could, and one of the questions that ZooScience was interested in was the sort of cyanobacterial bloom. So that was an optional data set as well. And that was, that option was due to trade-offs for data availability. So what's probably not lost on anyone here is that building these types of data sets is really, really hard. Um, and just to share how we went about doing this, we did send a template out to everyone, and so in that template was generally how we requested that folks contribute their data. Um, but some people get very creative in how they view that template. And so what was returned was we asked for this nice stackable disk, and we got wooden blocks, we got trapezoids. Some people sent their, many different shapes to the data were returned. And so that led to our team of about 30 largely volunteer folks, that ultimately had to shape and make each data set consistent internally, so that they could be consistent across data sets as well. And so, yeah, that's, when I say like it took, this is one slide that took, I think back of the envelope calculation was around 2,000 hours of just data cleaning. So, looking in hindsight, I'm like, oh, wow. And how the data are structured. Oh, there it is. Okay, how the data are structured is effectively in all these separate CSVs. And we did this largely to empower ZIG not only to be used for zooplankton data, but also empower various water quality analyses. So each of these CSVs represents, like, I guess what Hadley Wickham would call like an observable unit. So we have like water parameters, we have the zooplankton abundance, we have some zooplankton length data within ZIG, and then the sort of static variables like the water bodies, the station ID, and then a timeline where the data providers could say, was there a noticeable change in a specific year in your system? And they can give their sort of system-specific knowledge. And then also this taxa list, which ultimately harmonizes our data set with various global biodiversity information repositories, so like GBIF, IDIS, stuff like that, so that those taxa can then be linked to other data sets. And so the data sets that are in ZIG, so we have 311 lakes in 36 countries, 6 continents. And you can see that they span a range of these thermal regions, which is basically a definition of what's like the thermal phenology of that type of system. So it's a way of really getting at not only the magnitude of temperature of a temperature regime, but also the dynamics of the temperature regime that ends up being really important for these ecosystems. And one thing that I'm personally really proud of in ZIG is that we have good latitudinal representation. And you might be looking at this plot thinking like, what are you talking about, Michael? They're all at these like north temperate latitudes. This really isn't good latitudinal representation. Well, if we compare these latitudes with other global lake compilations, so here we have hydro lakes, which is this compilation of about 1.42 million lakes globally, lakes of at least 10 hectares in size. And if we compare the latitudinal distribution of hydro lakes with that of ZIG, we see that we're actually tracking pretty well the global latitudinal distribution of lakes. Maybe there's some underrepresentation of these northern cool ecoregions or thermal regions. But I think it's really, really powerful that ZIG represents the global distribution of lakes, so that even though we do have greater representation from these north temperate ecosystems, those are ultimately the most abundant lake ecosystem regions in the world. And so we really are able to talk about global lakes globally, at least on a proportionate basis. Okay, getting to that time series component, many of the time series within ZIG are at the monthly time step. 40% have at least 10 years of data. From 1 to 60 years of data are represented. Some are even at the weekly time step. And I think it's important that, just to really emphasize how uncommon this data repository is. 70% of lakes are at least weekly, fortnightly, or monthly. For those limnology nerds out there, a lot of the lakes are dimictic, meaning that they mix 2 times per year. Also tends to be pretty associated with those north temperate ecosystems. So we're not only getting the locational, or they also tend to be at about the same elevation status or elevation level. So we're not only capturing the lake locational and lake thermal region, but we're also capturing a pretty good range of the lake physical mixing processes that ultimately is associated and highly related with biological productivity. And then we're also capturing a pretty strong range of maximum depths and water body areas. So this is a long walk for the short drink to say we've got an impressive amount of lakes assembled within this data set. For zoo size, there's about 3,800 observations with a median of 1 observation per lake, max of 700 observations per lake. And there's the spatial distribution of the zoo size data set. Once again, capturing that north temperate system especially well, and also get a range of altitudinal gradients. Okay, so that was a really really quick way of summarizing 6-7 years of work. But once again, I just want to say thank you so much to ESIIL, as well as CISAB and the Powell Center. These are really the spaces that provided that atmosphere where we could really sit down together and felt so well, like not focus on the data and the thoughts that we need to make about the data, but ultimately what's the science that we can do with these data. And some high level findings that we've been, and I just want to give some high level findings about what we've actually been doing with these data sets. So I'll be talking about the ZIG work, and Rachel will be talking about the ZOOST team, or the space for time substitutions. So ZIG, what's been the main question that at least been, my wake up at 2 a.m. and think like, what are we gonna do with ZIG? Has largely focused around, this tapping into that zooplankton as indicators, but thinking also about resource use efficiency. We know that zooplankton are important for ultimately taking energy and matter at lower trophic levels, moving them to higher trophic levels. And what's the extent of our knowledge about that in that space? And there's actually this really nice review, HODA 2019, that looks at this idea of resource use efficiency across ecosystem gradients. And it's in I think in aquatic ecosystems we think about this a lot. I'm less familiar with terrestrial environments, but it's that story of a little bit of resource supply, especially in these low resource environments, tend to lead to a large increase in resource use efficiency. All those organisms they just suck up all those excess nutrients because it's a really low nutrient environment. And then you reach some point where the efficiency, or the amount of matter that moves from a lower trophic level to a higher trophic level decays, and then it kind of bottoms off. And this tends to vary with productivity. And so at least in our ecosystems, right, we're thinking about nutrients moving into phytoplankton, moving into zooplankton, and ultimately moving into fish. And many of us are so concerned about that fish part of this equation, but it's also ultimately contextualizing that part of the food web within all these other lower trophic levels. And so, we would love to be able to synthesize across all these ecosystems. How does resource efficiency vary across lakes, across latitudes, across ecoregions? But a lot of the indicators that have been built for associating zooplankton with those higher trophic levels, tend to be concentrated within those north temperate ecosystems, or specifically those Great Lakes regions. And Steph Figueri, the first author of the ZIG data set and the ZIG data paper, has done this a lot, looking at the Great Lakes. But for many folks out there, we know that there's many lakes that aren't Lake Superior or Lake Michigan, and they vary in what they experience, in their shape, in their altitude. So how does resource use efficiency, and how does I also think that community composition that's associated with use efficiency vary across these large scales? And we can actually use SIG to get at some of those questions. So if we look at I didn't update the title on this. I'm sorry, my bad. Uh, this is one of those things. Sorry. So what we can actually ultimately do, so ignore the title of this slide, but the figure is looking at the resource use efficiency. So remember, for many lakes, we have paired biomass data and community composition data, density data. And if we plotted resource use efficiency, so that's the biomass of zooplankton divided by chlorophyll concentration, or that phytoplankton, we see that these northern temperate systems tend to have higher resource use efficiency values. There's variation, but as we move down in latitude, we tend to go to lower resource use efficiency values. You can think about it, those ecosystems that like turn on, turn off. They have winter, and they sort of have these really high efficiency values. Okay, now genus level richness can be high at these north temperate ecosystems, but it's not necessarily as clear of a pattern. There's a lot of variation, especially at the genus level, moving across these latitudes. And one way that many folks have been getting at this is there's a lot of literature that's looked at Daphnia, this pretty cosmopolitan, pretty quick eating zooplankton. And so we've thought about looking at, okay, what's the relative ratio of Daphnia? That's what literature might tell us. And what we found is that Daphnia dominate about 2% of lakes, relative to calanoids, cyclopoids, bosmina. And one thing that I found really cool, Rachel actually led this work, was that if we compare how frequently we actually see Daphnia dominating in natural environments, it's 2% of lakes in ZIG. But if we look at how frequently Daphnia is referenced in like the dogma of limnological texts or Wetzel, we see that Daphnia represents about 71% of zooplankton referenced in limnology textbooks. So there's might be this mismatch between what we're actually seeing in the environment, how frequently we're seeing things in the environment, and how frequently we're seeing things in our texts. And so what we started to do was these sort of multidimensional or multivariate analyses where we look at community composition in respect to RUE. And when we look at those main zooplankton groups, we see that these calanoid copepods, so this one genus, very long-lived, tends to go down deep within the water column, comes back up, long-lived for zooplankton. So like we're talking about months. We're not talking about decades. But that taxa tends to be more associated with these high RUE values, whereas Daphnia, cyclopoids, they're less so. And actually, this sort of has an interaction with thermal regions. What we're starting to see is that at these north temperate thermal regions, we can actually use calanoid copepod density, relative density, at understanding median resource use efficiency, so that with an increasing calanoid copepod and these sort of I would say like seasonally strong systems with respect to temperature, we're seeing higher median resource use efficiency at the global scale. And one thing that I found really cool, I didn't include this in the slides, is that we actually compared these results against the US EPA's National Lakes Assessment, which is a US focused sort of ZIG analog. And we see strikingly similar patterns amongst the thermal regions that are within the US, the contiguous US alone. And so I think it's providing a really strong weight of evidence that these data are picking up on something very real And that calanoid copepods seem to be that like secret sauce in getting the high, or secret ingredient in getting that high resource use efficiency. And, also, especially at an agency where we talk about water quality a lot, I think it's really cool to say that the standard water quality metrics alone don't detail the same relationship. So in my job, we talk a lot about temperature. Temperature alone does not get you the resource use efficiency. So here we have mean surface water temperature from the ZIG data set. It's pretty much a flat line across when you relate that with ZIG or with RUE. Phosphorus, we kind of get a similar relationship. Um, However, it's less clear. I would say it's probably less clear. And it is also a nonlinear relationship, much like with the zooplankton community composition. But this is the sort of the long walk for the short drink to say, I think that adding in that biodiversity perspective really gives you a different understanding. And ultimately, when we did plug this into trying to understand when we were trying to model RUE as a function of these water quality parameters, adding in calanoid copepods only increased the robustness and the accuracy of those statistical models. So I do think that this is a very strong value add for many of our existing observing networks. And I think that sort of summarizes a lot of so maybe just to sum up, I think what we're able to do is not only use ZIG to look at community composition or sort of like the structure of the ecosystem but we're also using ZIG to also get in some of those functional questions, is how is energy moving between these trophic levels at the global scale and also outside of ecosystems where we've traditionally laid most of our foundations in the aquatic sciences. And so with that, I'm going to pass over to Rachel, who's going to share her slides about Zoost.
Thanks, Michael. Let me get this set up real quick. Awesome. So I'm going to talk briefly about one of the other projects in our ZIG universe called ZOOST, which stands for Zooplankton Over Space and Time. And the idea here is that we know a lot of ecological and evolutionary processes obviously operate over different timescales, whether it's very rapid over, minutes, hours, days, to longer term decadal patterns. And so ideally, we would use long-term monitoring data to understand how these patterns change or what interactions and other relationships we see in our ecosystems.
Rachel,
And
any gray Zoom boxes? I'm seeing them over my screen. I don't know if you folks are seeing in Boulder, seeing it over your screen. Do you know what I mean?
I do. Did that get rid of it at all?
That's better. Yeah.
Better. Okay. Can you still see like the majority of the slide at least?
Yeah.
Okay. Sorry about that. Hopefully you can still see most of the stuff on here. Where was I? So yeah, long-term data take a long time to accumulate. So oftentimes in ecology, including freshwater science, we use space for time substitutions where we take advantage of a lot of ecosystems that are very different and have a lot of character gradients in their characteristics and sort of assume that we can measure those characteristics over space and apply them and use them to project what we might see over time. One more second. One are a couple good examples of these long-term monitoring programs we have in ZIG and in our aquatic sciences are Lac Leman or Lake Geneva, which has data going back to the 1950s and shows a really nice trophic gradient or total phosphorus gradient over these multiple decades. And then we also have Loch Fia, which is in Ireland, where we've seen really strong warming across time since the 1960s. And so these are fantastic data sets to be able to understand long-term patterns, shifts in the ecosystem, and biological responses like zooplankton biodiversity. But these are fairly rare overall. So what we often do is look at trophic gradients across many different lakes that, of course, have different internal dynamics, have different watershed characteristics. And we sort of assume that these these patterns over space are going to mimic what we might expect over time, whether it's with trophic gradients or thermal gradients, temperature gradients, things like that. And so that's sort of the space substituting for time, where we don't always have long-term data sets. And we've used these space for time surveys quite a bit, including like the National Lakes Assessment, which Michael mentioned. This was actually sampled a couple of different years, but it generally represents snapshot data across thousands of lakes in the United States. There's a similar effort, the European Multi-Lake Snapshot Survey, or other studies who have looked at broader scale latitudinal gradients, typically sampled once or twice to kind of understand how these how response variables change across specific gradients. But the issue with space for time is that we have a lot of baked-in assumptions that really haven't been tested in a really fine way that can help us understand things like the causality and reproducibility and transferability of space to time. So questions like, does the timing or order of sampling actually impact our results and impact that reducibility? What can we really say about the causality? Because each ecosystem is pretty unique, and so the drivers might be different or might operate on different time scales, that substituting space for time might lead to some blurring of that causality. And then finally, questions about the transferability. Do the relationships we see over space actually we actually transfer them over time to make projections about our ecosystems or biodiversity on longer term timescales? And so we've started to explore this to understand if space for time is a valid method to understand observed biodiversity dynamics, including things like, how does the timing of sampling affect inferred patterns? Things like the diversity of our zooplankton, which varies between spring, summer, autumn, and winter, and its relationship with temperature. If we only sampled during the summer, for example, where a lot of lakes tend to get a lot of snapshot samples done, are we going to get a similar relationship versus if we sampled only in the spring or sampled across the entire year? How does that impact sort of our built-in relationship between temperature and biodiversity, for example? And if we do this across many lakes or many different subsamples, can we reproduce these relationships fairly consistently? Like, do all those temperature versus diversity regressions give us a fairly similar pattern? Or do they give us really different patterns that really lower our confidence in being able to extrapolate or project this space for time relationship? And so I will pretty quickly share some preliminary work that we've been doing with this ZOS project. We have a lot in the weeds going on at the moment that hopefully will lead to some cool advancements based on what I'm going to share today. But we've been looking a lot at the variability in Shannon H index, which is a metric of biodiversity. So we're obviously using the zooplankton biodiversity as our response variable in this instance, using ZIG, and then water temperature as sort of our driver variable. And we're going to use a subset of global lakes, which I'll talk about in just a second. And so we basically wanted to evaluate how that diversity versus temperature relationship varied if we assumed space for time surveys were taken doing some bootstrapping and permutations, and how that might influence our perception of this relationship compared to if, for example, we have actual time series. Can we do sort of a one-to-one comparison and get consistent results if we did this space for time versus observed time series? And I'll show an example from Lake Wingra in Wisconsin for that one at the end here. So to actually filter down to what we call like our usable lakes from the ZIG dataset for this, we filtered based on some pretty specific criteria to give us what we thought would be the most robust way to test this, including some pretty high resolution taxa identification to genus. That's pretty high resolution for zooplankton data, at least. We're looking for whole water column estimates and neglecting those that were just focused on the surface or specific layers, so we could get sort of a whole water column picture that was comparable across lakes. And we wanted lakes that had at least 2 years of data, 6 months of data each year with at least weekly to monthly frequency, so we could really start to parse out some of that variability both within and across years. And so this ended up leading to about 120 lakes of the data set, which was a pretty surprising amount, with pretty good latitudinal coverage, which again leads to a lot of variability in temperature and thermal regimes, but a lot of other characteristics across this data set of our lakes and watersheds varied pretty widely, which I think is a pretty important factor of this space for time analysis. And so if we take all of those lakes and just really quickly put in all of their possible relationships of Shannon diversity as a function of temperature, this is what we get, where each blue line is the empirical regression from all 120 of those individual lakes. And that dashed black line is sort of our overall picture. These are all the data from any season, any year, for all of those 120 lakes. And the distribution of the slopes of these generally is positive. There's a bit of variability around zero. But there are a handful of lakes that actually have a negative slope here. You can kind of see them popping out at this bottom part of our plot here. So we see general consistency overall, but there's a number of lakes that don't really agree with that. And so based on this sort of empirical relationship using all data possible from that subset of lakes, we wanted to actually do some simulations of space for time surveys by doing some resampling permutations from them, basically saying from these lakes, what if we, sent out a team and if we took a snapshot sample from each of these lakes, could we reproduce a fairly similar set of slopes overall? So using a bootstrap analysis, we did this for our first go. We just did 100 permutations of this. But conceptually, we can explore this by using these sort of Shannon diversity time series from 3 example lakes here. And they, of course, vary quite a lot over multiple years, over the seasons within year. And so for our first permutation for all of these lakes, we were randomly selecting one snapshot survey of any time in the entire time series, calculating the Shannon's diversity and regressing it against temperature. And then, we'd end up with some regression slope. We'd repeat this completely new set of samples. Maybe it was from a different time, maybe it was from a different season, totally random new set of samples for permutation number 2, and then regressed our diversity index at that time point with the water temperature at that time point, giving us a slope number 2. We repeated this 100 times for all these different permutations and then got this collection of different slopes of our diversity by temperature relationship. And so again, if we have a lot of similarity in these relationships, we can say a lot about the high reproducibility and transferability potential of this type of study when we're specifically looking at temperature versus zooplankton diversity. But if we see a lot of differences and inconsistencies in this bootstrap analysis, that really reduces our confidence in reproducibility, transferability. And so here's the example of that 101st set of permutations that we've done, again, across all lakes and seasons. We didn't do any subsetting for time frames quite yet. But each of these black lines represents one of our 100 permutations. And this is the distribution of our slopes in this sort of gray boxy plot at the top. And you can see that almost all of our slopes are positive with a pretty big range. I think there's just 2 that actually fall out as negative slopes. So fairly consistent in the overall direction of slope, but more variable in terms of its magnitude. And so there's one lake, Lake Wingra, that I mentioned earlier that has a really nice time series that we started to actually test to see how does it actually compare if we use this space for time permutation study, how does it actually compare to the time for time data that we have in a lake like that? And so just for reference, Lake Wingra is there, the slope just for that lake is falling out at this part of our distribution. But here on the top, we have our Shannon diversity time series, and the bottom, we have our temperature time series over many, almost 2 decades. And you can see there's a lot of cycling in there, a lot of relationships where these values are high during the summer, low during the winter. If we regress them, temperature versus diversity, this is the relationship we see. Again, it's right about at this 0.2 mark, this somewhat higher end of any of our permutations. And to actually assess our precision and how well we could predict this time for time relationship using this space for time permutation, we took all of those permutation regressions and just did a predict function. And we basically calculate our root mean squared error as a function of that. So here are 4 example permutations that are represented by one of these lines and the resulting root mean squared error of our predictions specifically for Lake Wingra. And there's a good amount of variance here. B78, we picked this. That's one of our negative slopes. You can see the root mean squared error is quite a bit higher there. But if we looked at these over all 100 permutations, this is the distribution in RMSE we would see, again, using all lakes, all seasons, and trying just to predict this Lake Wingra time for time relationship. But then we thought, well, this set of global lakes includes a lot of lakes that are really dissimilar to Lake Wingra, which is a North Temperate Lake in Wisconsin. So what if we actually subset our set of permutations and ran this analysis again with only lakes that are, geographically and thermally more similar to Lake Wingra? So then we subset this to only including lakes in US and Canada that were at latitude 38 degrees or above, generally those North Temperate, northern cold systems. And we reran our permutation analysis exactly the same, and these are the results that we get. In this instance, we get 100% of our slopes are positive, but the magnitude of those positive slopes actually is a much more variable than we got when we looked at our global set of data. And then if we do our prediction functions and we look at our root mean squared errors only from the regional lakes, we actually increase that root mean squared error. We don't increase our precision at all. And so that suggests that there's a lot of variability in these global lakes that we can take advantage of that actually might improve our predictive power rather than trying to subset to lakes that are more similar to our focal lake, because we kind of lose that maximal variability that seems to be helping, at least in this one instance. We've got a ways to go yet. And then the other thing that we tested was potential for seasonal differences in this temperature biodiversity relationship. All the data I showed previously was just looking at all times of the year, all months. But what if we break these down by sort of our 4 typical seasons? Because zooplankton life cycles and zooplankton phenology varies a lot from spring, summer, fall, and winter. So we did our same permutation analysis, but first by subsetting by our 4 seasons. And if we look at just springtime, these are our permutation relationships and our distribution. Almost all of these, again, with the exception of just a couple, are positive in direction with a fairly small range in magnitude. If we did the same thing for summertime, we get a very different story where we see a lot sort of flatter distribution centered around 0, where maybe half or so are positive, half or so are negative. And there's a much bigger spread in that direction and magnitude if we just look at summertime. Summer's a really dynamic period for lakes. So sampling at the beginning of the summer versus even 1 month later can have an entirely different zooplankton community and therefore totally different zooplankton diversity. If we look at autumn, we start to see more negative relationships with temperature, very opposite to what we see in spring. And then in wintertime, we kind of get a little bit more of a mixed bag where the majority of our relationships are positive, but again, there's a lot more variability around 0 compared to springtime, for example. So this has suggested to us that looking at seasonal dynamics not only influences our space for time relationships, but also could be important in how we actually project in the future, depending on what time frame of interest we're really looking for. And so we're excited to set up and more deeply evaluate the space for time and time for time together, because within our ZIG dataset, we have a lot of time series. One great example is Lake Oneida, which is one of the Finger Lakes up in New York. It also has this really, really fantastic time series of zooplankton, and we can calculate Shannon diversity at the sub-monthly scale for multiple decades, which is absolutely insane. And so we're hoping to do similar analyses and comparisons as we did with Lake Wingra to lakes like Oneida, especially because there's some unique disturbances to this lake that we're very interested in seeing how they sort of fall out in our comparisons and if they skew our space for time projections. Things like a zebra mussel invasion in the 1990s and just a few years ago, a Bithotrophes invasion that really depressed the overall diversity, at least for a few years. And I think Michael mentioned this before, but over 40% of the lakes in the ZIG dataset have at least 10-year time series, which can be really valuable for assessing these space for time substitutions and even helping us determine what lakes or what types of lakes might have more valid space for time substitutions compared to others that maybe are a lot more difficult to have that substitution and feel like you can reproduce it and transfer it effectively. And so some of the sort of higher level things that we're thinking or that we're planning to do and a little bit in progress are looking at these relationships across space and time. And if they're in the same direction with a similar magnitude, we have a lot more confidence to say there's a causal effect and there's some transferability there. Whereas if they're not in the same direction and not the same magnitude, these probably are responding to different processes over space versus over time and give us a lot less confidence in our causality of whatever 2 variables of interest we're regressing. But if they have a similar direction and maybe slightly different magnitudes, we can probably suggest that maybe these just aren't in equilibrium versus space or time. Maybe there's a biotic lag temporally that our spatial analyses can't pick up, or some sort of offset or change under future climate in a nonlinear way that, again, our space substitutions are just unable to pick up because it's sort of a unknown temporal time frame. And so I will quickly wrap up so I can leave just a little bit of time for questions about some final thoughts with our ZIG dataset, which has been a pleasure to work on. It is a treasure trove of data. And with a couple of the analyses we've started and presented today, we've barely scratched the surface with the types of things that we think this dataset can be useful for with zooplankton and community composition and biodiversity and all the water chemistry and water quality data that it has. As Michael mentioned, it has not always been an easy journey, starting from the compiling and harmonizing data sets. It's been a great team to work with. That's required a lot of time and patience, as probably all of you who've done something like this recognize. But having dedicated time at ESIIL has really, really helped us get focus time to actually hash through so many things that otherwise are kind of just like a side project for our normal work life, where we don't have dedicated time throughout the workday, most of us at least, to spend on this. So having this dedicated working group time really felt like we were able to advance things pretty rapidly in just a week. And of course, like ZIG and all similar data sets to it, whether they're, freshwater related or not, we can start to address really important questions about biodiversity and ecological change at regional and global scales, kind of going beyond the couple of lakes that are in your backyard or the couple of ecosystems near you, to really understand how some of these big ecological changes and processes could be affected by, future climate and other anthropogenic stressors. And so I will end with a quick thank you once again to ESIIL and all of our other funders and all of the folks who made this work possible. And I think we will have a couple minutes for questions.
You heard us. All right. Does anybody have some questions? And if you're online, feel free to unmute or add your question to the chat.
I have a question. I didn't realize that the lake distribution was so biased towards the north, so I learned something there. But it's also really cool that even beside that bias, you were able to show some classic latitudinal patterns, which is really cool. I constantly, through the whole thing, was thinking about the Rift Valley lakes and the cichlid, sort of massive radiation of cichlid diversity, and I was curious if you found any weird spots like that. Were there any weird spots in the world where we're getting big radiations or weird stuff's happening for any reason, or is everything sort of falling out latitudinally like you expected?
I'm not sure that we have analogs to the Rift Lakes, like the cichlids, but maybe one thing is, in a previous working group meeting where we talked about, would we talk about biodiversity and would we talk about how we were looking at zooplankton biodiversity with this main ZIG synthesis, and at the time, at least, we consciously made the effort to exclude rotifer diversity, so those non-crustacean zooplankton, from the analysis, just because they were less abundant in the contributed data sets, and they're much smaller. Mesh size of the net becomes really important, so it's hard to compare. But one thing was, one of our colleagues in the working group is from Brazil, or tropical ecosystems expert, and she was like, at these tropical ecosystems, it's the rotifer diversity that becomes really important. And I think it was that moment that made us step back. And so it's not to say there's anything that was abnormal or surprised us, but I think making sure that we're taking our research bias into context. Not only are many of us influenced from strong North Temperate Lakes background training, largely because there's a bunch of lakes there. But we're also influenced by the taxa that we tend to work with and we tend to think about that tends to be in those ecosystem types. So I think a big takeaway was like, yes, we're applying a lot of metrics that we've been thinking about in those types of ecosystems. But what if we included the taxa that tend to be more representative of these tropical ecosystems like rotifers? So that's not a one-to-one, but I think for me that was a big takeaway. Rachel, did you have other thoughts?
No, I think that's a really good answer because there's probably a number of lakes that do have like unusually high diversity that I don't think we've necessarily like pinpointed or actually like looked into quite yet. We've kind of just been looking at sort of higher level patterns so far. But it would be super interesting to know, even at the like the crustacean, the non-rotifer zooplankton, what lakes or if there's something unique about them or similar about the ones that have the higher diversity. If we could explain that, but I don't think we've gotten to that sort of individual lake look quite yet.
Cool. So cool. Thanks for sharing, guys.
And there is a question in the chat. So what do you think explains those few lakes with decreasing diversity at increasing temperatures and our warmer tropical lakes reaching high temps, phytoplankton blooms, or something else?
A fantastic question. I couldn't even tell you which exact lakes had the 3 or 4 empirically negative relationships offhand. So another point, kind of like I just said, like we haven't looked at the individual lakes to kind of figure out what's special or unique about those yet. But your suggestions would be things that I would be thinking about because in a lot of systems, even if they tend to be a colder lake on average, like the community is more adapted to colder temperatures. So when it reaches a certain point, a cold adapted community can still see a drop off in diversity when it reaches, whatever its sort of community temperature threshold is. That certainly could be the case in tropical lakes too, where, there's obviously a temperature where everything is going to sort of metabolically shut down. I don't I think phytoplankton blooms could also play a role. I'm not enough of a phytoplankton or algal bloom expert to really know if there are obvious triggers for that we have in our data set that we could assess, or if there would be um, like an obvious reason those could decrease diversity of zooplankton specifically, rather than like they're often associated with like low oxygen where fish kills could become a problem. I'm not sure offhand how the zooplankton respond besides having less quality of food, so that could be something to look into. I think we have a couple phytoplankton oriented folks in our group. Yeah, Michael, if you have anything to add, please.
The only thing I would add is I think a fun spin-off project that came out of our ESIIL working group was what's called Zoothermo, and they have their own logo. And what they've been using is sort of the co-occurring zooplankton and temperature data to understand the thermal niche that we're seeing in actual ecosystems. And one thing that, if I'm remembering correctly, what Ichiro was finding was that kind of counterintuitive is that some of these zooplankton seem to be moving to colder ecosystems and being more associated with colder environments. So I think that there's a lot of like open range for exploring that analysis, especially for understanding like thermal plasticity of different taxa. So yeah, wide open space.
All right. Any other last questions? Okay, I'll do a fun.
Can I ask one? Let me ask one more. You've articulated this a couple times of what ESIIL did to help you with the science. Could you just one last time give us a summary of what did ESIIL do that allowed you to do this, or what could you have not done without ESIIL?
I think my salient message would be really providing the space for us and dedicating that time where we could be like in this highly interactive dynamic space and just dedicating that time. That that to me was like the difference between like, is this done this decade or uh, this millennia? Yeah, Rachel, did you have any?
Yeah, I think that's probably the most important because I think I mentioned a lot of us don't have like dedicated time in our normal work hours to spend on this. And so being a side project, like I'm going to work on this like an hour a week, like that's not going to get traction. And so getting all of our brains in the room to like look at the data, harmonize the data, and like just do the things in a completely like undisturbed environment with, 10 or 12 of us. I think that made all the difference in making like our data products, our data papers, the and beginnings of these analyses actually possible to get some traction.
Sweet. Thank you so much.
Thank you.
Thank you.
Thank you both. It was great to see you.
Likewise.